Well, we'll see how the scores turn out. Key will soon be posted. And just as a reminder, exam 2, a week from tomorrow. Usual time arrangements. Starting 8:20 p.m., we'll let you work till 11. And for those of you who have the Thursday conflict, which I will presume is most, if not all of you from exam 1, since we also did that on Thursday, same arrangements. Take exam 2, earlier in the day for the conflict people in Lee 309. Except that this time we can start at noon. So if you wish to start at noon on Thursday rather than 1 p.m., which was the earliest possible starting time for exam 1, let me know. And I will still want a note or some sort of a reminder from you folks if you did exam 1 earlier and you're also going to do exam 2 earlier, just so I know what's going on. So, more on analysis of equilibrium systems which contain salts of limited solubility in water. Question 1912, which we led into by way of last conversation. Let's compare the solubilities for calcium sulfate, calcium carbonate in a water solution buffered at pH 6. Now, given that we did the analysis in detail last time for calcium carbonate water solution buffered at pH 8, we know for sure calcium carbonate is going to be more soluble even than it was at pH 8, now at pH 6, because this is a 100 times more acidic system than pH 8. So hydrolysis of bicarb ion to H2CO3 must now be considered, which we also showed last time. Which really is the chemistry reason why the solubility of calcium carbonate is much greater at pH 6 than it is at 8. We'll look more at that analysis in a moment. The other part of the issue is at pH 6, does the Bronsted-based sulfate ion, the anion component of calcium sulfate, hydrolyze extensively? Show its ability to behave as a Bronsted base extensively. That's the same question. Because hydrolysis involves reaction with water. And when sulfate reacts with water, as our reaction equation indicates, we're looking at Kb sulfate, hydrolysis of sulfate. Products, hydrogen sulfate ion and hydroxide ion. Well, to get a handle on this, we consider Kb sulfate, which is 8.3 times 10 to the minus 13, a daggone small number. This is already suggesting that hydrolysis of sulfate ion isn't particularly consequential. The question is, how consequential is it at pH 6? Well, here's the equilibrium constant expression. I have rearranged it so as to generate a concentration ratio at equilibrium of sulfate ion to hydrogen sulfate ion, which is hydroxide ion molarity divided by Kb at pH 6. This is the hydroxide ion molarity, the 2 sig figs. Here's Kb, 12,000 to 1. So what's this telling us? 12,000 of these for every one of these. Hydrolysis extensive? No, practically not at all. In fact, if you look at this, you can see that this is going to have to go down at least to pH 10. I mean, pardon me, not pH 10, but pH 4, so that this will be 1.0 times 10 to the minus 10. In order to get a ratio of sulfate to hydrogen sulfate, which might require you to consider the hydrolysis reaction. But any system at a pH higher than 4, even 4 is sulfate hydrolysis is negligible. So I wrote that over here. Therefore, based on this analysis, the solubility of calcium sulfate at pH 6, or really any pH 4 or above, is square root of KSP, because hydrolysis of sulfate is nothing to speak of. There's KSP, there's the solubility. All right. Now, how will the solubility of calcium carbonate at this pH compare? Well, let's proceed with the analysis. We recognize that at pH 8, this equilibrium reaction does a very good job of representing the chemistry that occurs when calcium carbonate is saturated in water solution buffered at pH 8. Well, how about at pH 6? Well, we can still use the same equilibrium reaction as long as we recognize that this may well not be a stoichiometric statement. So we write this is K. We know the calcium ion molarity is equal to the solubility. The question is, how does the bicarb molarity compare to the S value, the solubility, at pH 6 in this case? We found out that bicarb molarity was practically speaking the same as S at pH 8, but pH 6 is a different story. Times the hydroxide ion molarity, which at pH 6 is 1.0 times 10 to the minus 8. So if we can figure out how at pH 6 the bicarb molarity relates to S, then we will reduce this equation to one unknown, namely S, and solve it for S. So I wrote this is our question, and as we did before, to resolve the issue, because what we're looking at is all possible forms of carbonate containing things as a function of pH. And to get a handle on this, we can use Ka bicarb as well as Kb bicarb. Ka bicarb relates to the equilibrium molarities of bicarb and carbonate ion. Well, here's the Ka bicarb, which we looked at last time. Remember at pH 8, this ratio was 210 to 1? We take it to pH 6, it's 21,000 to 1. Because the more acidic the system, the more effectively you kill carbonate ion. Because carbonate ion is the strongest base of consequence in this system. Certainly the strongest base of consequence for carbonate-containing things. So at this pH 6, forget carbonate. Look at this concentration ratio. But how about quote-unquote H2CO3? Now we go to Kb bicarb, just like we did last time. At pH 8, the bicarb molarity compared to quote-unquote H2CO3 molarity at pH 8 was 42 to 1. We looked at this last time. We even made a comment about that compared, in relation to this last time. Now, at pH 6, hydroxide ion molarity is this. There's Kb bicarb. And so we see that at pH 6, the predominant form of carbonate-containing stuff in the pot is this stuff. But this is also a species whose concentration must be considered. The concentration ratio is 1.0 to 2.4. Or, this is telling us that the H2CO3 molarity is 2.4 times that, the bicarb molarity. All I did was rearrange this to get that. So, as we said, this is telling us the predominant form of carbonate-containing stuff at pH 6 is this stuff, but this stuff is still a species whose concentration must be considered. But now we can relate bicarb molarity to S, because we now know how these compare. This, rewritten, plus this expressed in terms of molarity of bicarb, 2.4 times bicarb. So what do we find out? S in terms of in terms of carbonate containing things, S is 3.4 times the molarity, equilibrium molarity of bicarb for the system buffered at pH 6. Put that in. Bicarb in terms of S. S divided by 3.4. Solve it for S, you get 2.1 times 10 to the minus 2. So if you go back and re-examine the data points which we have collected for the soluble carbonate as a function of pH in water solution. You see, this is by far calcium carbonate showing us its highest solubility. As we know, because, doggone it, the previous systems considered were saturated in deionized water where we've got a pH of 10, buffered solution at pH 8 last time, and now buffered solution at pH 6. Progressively getting the system more acidic means the molarity of calcium carbonate is going up, up, up. In fact, practically speaking, below pH 6, you cannot succeed at getting carbonates to precipitate with any particular degree of effectiveness. You accept that statement? At pH is less than 6, practically speaking, you cannot get carbonates to precipitate with any degree of effectiveness. Because if you're going to get carbonates to precipitate effectively, you've got to have a reasonably high molarity of carbonate ion. And you can't get that at pHs lower than 6. Carbonate is murdered too much. See, we did that over there. Now then, just to show you that the carbonate ion, we got it here on a concentration ratio basis. What if we wanted an absolute value for the carbonate ion molarity at pH 6? How could we get it? So I wrote this question here. What's the quickest way to calculate the carbonate ion molarity? pH 6. I'll extend this question to read based on above, that which we have just done. Perhaps you do this on quiz or exam. What are you going to do? The quickest way to get the carbonate molarity for a system in which calcium carbonate has been dissolved to its maximum extent. We saturated the solution with calcium carbonate at pH 6. We've got a calcium carbonate molarity of 2.1 times 10 to the minus 2. What's the quickest way to get the carbonate ion molarity? Initial molarity. That's its initial molarity. We want the equilibrium molarity. Do you understand what I'm saying when I say that's its initial molarity? I wouldn't. I want the quickest way. Because if I use KB, I got to get the bicarb molarity calculated too. Yeah, I'm lazy, but I want to be effectively lazy. Being effectively lazy means you do it right, but you do it the simplest possible way. Nope. How about this? What's this concentration product equal? What is it? KSP. How about that? And what's its value? 2.1 times 10 to the minus 2? Boy, this is tough. You divide that by this and you got it. Well then, let's take a look at this. What's 6.2 divided by 2.1, roughly? What is it? 3. That one not hard, is it? What's 10.9? 10 to the 0.9. 10 to the minus 9 divided by 10 to the minus 2. 10 to the minus 7. There you are. Carbonate molarity is 3 times 10 to the minus 7. Whoop-de-doo, that's damn dilute. That's a damn small carbonate molarity. Look at the relative molarities of carbonate to calcium ion. Or the relative molarities of carbonate ion to bicarb. Or better yet, the relative molarity of carbonate to H2CO3. Carbonate is, practically speaking, non-existent at this pH. That's why making carbonates, precipitating carbonates at pHs less than 6 is practically impossible. Because carbonate is too effectively attacked by acid. Now that's a loaded statement, what I just said. Because if you extend that statement without thinking about further chemistry and apply it to the solubility of sulfides, you might well conclude, hey, how can I make a sulfide precipitate at pH 6? Well, when you folks get to assignment 7 and 46L, you will discover that if you make zinc sulfide, you can get it to dissolve with 1 molar hydronium ion. That's pH 0. But if you make silver sulfide or copper sulfide, as you will make in assignment 7, you'll find out that copper sulfide and silver sulfide laugh at hydronium ion at pH 0, 1 molar hydronium ion. You still won't bring about any effective dissolving of silver sulfide, copper sulfide at pH 0. Even though sulfide ion is a stronger base than carbonate ion. Because the bonding between silver ion and sulfide ion and the bonding between copper ion and sulfide ion is a hell of a lot stronger than the ion-ion bonding between calcium ion and carbonate ion. And what we're looking at is something we'll talk about rather extensively in a few more weeks down the road, when we start talking about the chemistry of transition metal ions and start recognizing that materials like silver sulfide and copper sulfide are not ionic at all. Even though these materials are made by the combination of ions, after you make the interaction, after you get after you get sulfide ion interact with silver ion, or sulfide ion interact with copper ion to make silver sulfide and copper sulfide respectively, you got a material which becomes highly covalent in character. And in the world of chemistry, did you learn this in 2045? Of the various types of bond interactions, which are the strongest? What are the strongest bonds? I'm listening. You didn't get this in 2045. Covalent bonds are the strongest. Yes, indeed. And that relates to why silver sulfide, copper sulfide, independent of hydronium ion molarity, cannot be dissolved effectively. More on that later. Okay. Now then, Next question. You're in the laboratory. 46L. You want to find out if a solution's got calcium ion in it. The solution does contain sodium ion. So a flame test cannot be used successfully because the sodium ion flame predominates. You have observed solution pH for your unknown sample and found it with indicator analysis to be on the order of 6.0. Okay so far? You're looking at an unknown sample which in water solution shows a pH of about 6.0, which you have determined by indicator analysis. And you want to find out if it's got calcium ion in it, yes or no. And since flame test is ruled out, you've got to go after calcium ion by precipitation. So you go to the side shelf. And there before you stands sodium sulfate solution, half molar, sodium carbonate solution, half molar. Which one do you use? Sodium sulfate solution, half molar. Sodium carbonate solution, half molar. The solution of choice will be added to the test solution to see if you get a precipitate. If you had sulfate ion, you get calcium sulfate. If you had carbonate ion, will you get calcium carbonate? Unknown solution. Gee whiz, pH is 6.0. What are you going to grab? Sodium sulfate solution or sodium carbonate solution? How many grab the sodium sulfate solution? How many grab the sodium carbonate solution? Well, I'm keeping my hand up because I'm grabbing the sodium carbonate solution. Why? You think that unknown solution you prepared in the laboratory is a buffer? It's no buffer, is it? So as soon as you start popping carbonate ion in there, the pH of that unknown solution goes zip. It's not buffered. And you don't have to raise the pH much to make calcium carbonate less soluble and easier to form than calcium sulfate. That's a dirty question, isn't it? And I just asked you. But I asked the question to see if you got your thinking caps on when you're in a laboratory doing laboratory work. That's what you got to do. If you understand the chemistry that 46L wants you to learn and understand, any unknown analysis which is issued for you can be done successfully in about 20 minutes or less. That's both samples. What do you think I say to students when they come to me with the complaint, I could have done this if you'd given me more time? When you got 2 hours. There's more time. Your problem is you don't know what the hell's going on. Now I have to be careful. I can't say what the hell, because the student might run off to the damn dean and then I'm in trouble. I don't have much patience with people who don't pay attention to material they're supposed to learn. I don't have much patience with those people at all. But I have great patience with those who recognize that it's difficult to learn and they come and ask questions in order to learn. I'll work with students like that. But if you're not here to learn, you better stay the hell away from me. I mean it. But if you're here to learn, you're with the right guy. That's it. I think you know that already. Okay, and now we go to the final issue raised in chapter 19, which is really just a takeoff on stuff we've already been doing. If you will, take a look at page 1913 in the notes. I'll write this down. Alteration of S by chem methods. As I said, we've already been doing this. Every time we change the system pH, we've been changing the chemistry of the system. So I'll title this as something else when I rewrite these notes. If only I could find the time. But I will somehow, some way, someday. In any case, we have offered you a statement on page 1913, which is important. So I want you to look at this statement on page 1913. So I don't have to write it on the board. I want to talk about it. It says, important statement. Bold, ital. The solubility S of any soluble salt with a basic anion is always greater in acidic solution than it is in pure water. And then comes the part of this statement that should be underlined. See where it starts with provided? Underline that to the end of the sentence. Provided that the acidic solution is not a precipitator of the salt. Point. Recall, if you will, the comments we just made about silver sulfide, copper sulfide, those materials being extremely stable. Because of their extreme stability, I can readily precipitate copper sulfide from solution or silver sulfide from solution by taking the silver ion containing solution and treating it with H2S, which is acidic. So if I got the silver ion swimming around in a solution at pH 7, or if I got the copper ion swimming around in a solution at pH 7, well, I can't get that with copper ion. It's too acidic. But I can get silver ion swimming around at pH 7, like silver nitrate solution. I bubble H2S in there, which clearly makes the solution more acidic. Wham! Out falls silver sulfide. Because H2S is a precipitator of silver sulfide. Or of silver ion as the sulfide, if you prefer. Let's do a simple demonstration of this statement before we take a look at calculating the solubility of calcium carbonate in ammonium chloride solution. Because before we do any calculation of the solubility of calcium carbonate in ammonium chloride solution, we know the calcium carbonate is going to be more soluble in ammonium chloride solution than calcium carbonate is in water. Because ammonium ion is a stronger acid than water. It's not a strong acid at all, but it's a stronger acid than water. And chloride ion is not a precipitator of calcium ion. So the system we're going to look at is the system that's on page 1913. Okay? S, calcium sulfate in 1.0 molar sodium hydrogen sulfate solution. You folks in laboratory have done investigations on the pH of sodium hydrogen sulfate solution. What'd you find for the pH of 10th molar sodium hydrogen sulfate solution? 10th molar. Because I believe that's the one I asked you to investigate at the tail end of assignment 2. Anybody remember? pH of sodium hydrogen sulfate solution at 10th molar. Two. For 1 sig fig, it's 2. 1 molar sodium hydrogen sulfate solution has a pH of 1 to 1 sig fig, as we shall now demonstrate. There's what you got to deal with to calculate the hydronium ion concentration as well as the sulfate ion concentration in 1.0 molar sodium hydrogen sulfate solution. Because you're looking at hydrogen sulfate ion plus water, double arrows, hydronium ion, sulfate ion. That's what you're looking at. And this is a single solute system. So the hydronium ion molarity and the sulfate ion molarities will be equal. Thus we can use that. X is sulfate ion, X is also hydronium ion. Okay? This gives hydronium ion, which is equal to sulfate ion of 0.10. Well, hydronium ion at a molarity of 0.10 is pH 1.00. There it is, right on the nose. Okay? The question then is, how about the solubility of calcium sulfate? Because this solution is considerably acidic. pH is 1.0. Now the solubility of calcium sulfate in straight water, we've already got it here. Here it is. It's the square root of KSP. There's the solubility in straight water. So the question is, what is the solubility of calcium sulfate in this solution, which has a pH of 1.0, 1.00 to 2 sig figs, compared to 3.0 times 10 to minus 3, which is the straight water solubility of calcium sulfate? Well, KSP is this times this, which is 9.1 times 10 to the minus 6, which is S, calcium ion molarity. But, as we have just demonstrated, in 1.0 molar sodium hydrogen sulfate solution, which is a solution of appreciable acidic character, pH is 1.00. What's the sulfate ion molarity? What is it? 0.10. Right there. So what's S? This divided by 0.10. That's 9.1 times 10 to minus 5. How's 9.1 times 10 to minus 5 compared to that number? Which one is smaller? That one. So even though that solution is considerably acidic, calcium sulfate is less soluble in that solution than it is in straight water, because that solution is also a precipitator of calcium sulfate, as we have just demonstrated. So the purpose of this was to show you the meaning of the part of this statement in bold, which I told you to underline, provided that the acidic solution is not a precipitator of the salt. Question 1913. Same page. The solubility of calcium sulfate in 1 molar sodium hydrogen sulfate solution, which we have just calculated, is essentially the same as its solubility in 10th molar sodium sulfate. You believe that statement now? Because in 10th molar sodium sulfate solution, what's the sulfate ion molarity? That's a tough question. It's 10th molar. Same thing, right? Okay, so on we go. So I'm going to write question 1914. And I'm going to write this directive. Ignore question 1950. I'm right now doing research on question 1950. And I haven't resolved the research yet, which will provide me with an experimental answer to question 1950. And I'm pretty sure the reason why I have yet to get the answer to question 1915 from an experimental standpoint is because of the complications introduced into analysis of water solution systems because of activity. So we're not going to worry about that. So in this case, you got to pay attention to what we are talking about, specifically and directly. Ignore question 1950. Question 1914 really is this. SCaCO3 in 1.0 molar ammonium chloride solution. As we said, before we do any arithmetic, we know the solubility of calcium carbonate in our ammonium chloride solution has got to be greater than its solubility in straight water, because neither ammonium ion nor chloride ion brings about precipitation of calcium carbonate, but ammonium ion is a stronger acid than water, so it'll kill carbonate ion more effectively than water. So for starters, what equilibrium reaction would you like to write to pursue this analysis? And you already know. At least I hope you know. And never forget that if you're going to start writing equations for reactions on a chemical system, what do you do first? How about that? Pay attention to what the hell you got before you start writing reaction equations. So now I got calcium carbonate mixed up with ammonium ion and chloride ion. And ammonium ion attacks carbonate ion more effectively than water, doesn't it? Because it's a stronger acid than water. So what I should write is this. This will be the principal equilibrium reaction of consequence established when I saturate 1.0 molar ammonium chloride solution with calcium carbonate. Well, if I'm going to do calculations on this, I need K. So I'll write K. Calcium ion molarity times bicarb molarity times H3N molarity divided by H4N plus molarity. And then I will go about the business of evaluating K by recognizing the fundamental Ks of which this equilibrium system is composed. What shall I recognize it to be composed of? How about KSP, calcium carbonate? Damn right. Carbonate ion becoming bicarbonate ion. How about KB carbonate? Damn right. Ammonium ion becoming ammonia. How about Ka ammonium ion? Damn right. So I know what Ks I'm looking for, don't I? I got to put them in properly. So your task is A, calculate K. It's in the notes. But if you want to do yourself a favor, you'll do it without looking at the notes. And B, here's the fun question. For this system, how do you think at equilibrium for this system, how do you think and why do you think it? The molarities of calcium ion, bicarb ion, and H3N ammonia compare for this system. How do you think the molarities of those three components of this equilibrium system compare? That's the question. And I shall expect everybody to answer that question when I see you on Friday. Because I'm going to send you all to the board to write the damn solution down, right?